In this lecture, we focus on how to learn the parameters of the mixture model from an observed sample of observations. We have already discussed the likelihood function. That will be the key component for us learning the parameters of the model. And we will be discussing two algorithms in this course. The first algorithm that we will be discussing, that is today's focus, is the expectation maximization algorithm. The expectation maximization algorithm is a very popular tool for computation in statistical modeling that relies on the presence of hidden variables. In our case, the hidden variables or the missing variables are going to be these component indicators that we introduce to create the complete data likelihood that we discussed in last lecture. So the goal of the expectation maximization algorithm is to generate maximum likelihood estimators for the parameters. So our goal today is to construct maximum likelihood estimators, MLEs, for the parameters in the model. And those parameters are the vector of omegas and the theta sub k parameters of each one of the components in the mixture. So remember that we define the likelihood function for theta 1 up to theta capital K and omega 1 all the way up to omega sub k as the product over the observations of the sum over the components of omega sub k g sub k of x sub I given theta sub k. The maximum likelihood estimators, which we're going to denote by theta hat, sub k and omega hat sub k, are just defined as the values of the different parameters that make this function as large as possible. As you may remember, the interpretation or the intuition for that is very clear. So if we think that this is the model or that a particular set of values correspond to the model that generated the data, then those parameters should be making the probability of what we actually observed be as large as possible. So just to make it compact, I'm going to define the maximum likelihood estimators of theta 1 up to theta capital K and omega 1 hat all the way to omega hat capital K as the argument of the maximum over theta 1 up to theta K and omega 1 up to omega capital K of this likelihood function that I wrote up there. Now, in principle, you could use any optimization algorithm that you like to solve this optimization problem and get these parameters. It's clear that there is no easy, simple closed form solution. If you take first order derivatives of this function up here with respect to different parameters and you make them equal to 0, you will get a very large system of equations that is clearly nonlinear for most circumstances. So you will have a really hard time solving that problem. With the additional complication that there are constraints that you need to respect for the omegas. In particular, you know that the omegas add up to 1, so you need to take that constraint into account when you are solving the optimization problem. So just brute force direct approaches to optimization are not going to be a good way to solve this problem because of both the high nonlinearity that arises from this expression and because of the large number of parameters. You have as many, so you have one weight in potentially p parameters for each component of the mixture, so dimensionality is very high. So what we will be discussing is how to use this expectation maximization algorithm as an alternative tool to solve exactly this problem instead of using some other numerical approach for this big dimensional problem. And one of the advantages of this algorithm is that what we end up with is a very simple approach in which the individual optimization problems that need to be resolved are very simple and can be solved in closed form for many expressions of G sub k that arise in practice. Before we go into the details of how the expectation maximization works for mixture models, let me just give you a quick reminder of the algorithm in its most general form. For the expectation maximization algorithm, we have an iterative process. And what we're going to do is we're going to start with some guess about what the parameters are. So in this case, our parameters are thetas from 1 up to k. And I'm going to use the exponent with parentheses to represent the iteration number. So you're going to start with an initial guess of what those parameters values are. So these are your initial values. And your algorithm is just going to proceed to update these parameters sequentially. So from this, we're going to construct a theta 1, 0, all the way to theta capital K 1, 1, omega 1, 1, omega K 1. And so on. So then we'll construct a second set and a third set. And each set is constructed based or using the values of the previous set as a kind of a starting point. And it's called an expectation maximization algorithm because it has two parts. So in the first part, we compute an expectation that allows us to generate a function that then is the one that gets maximized. So the way in which we're going to proceed is we're going to compute theta 1 in iteration s plus 1, all the way to theta capital K in iteration s plus 1, omega 1, s plus 1, omega capital K at s plus 1 as the arc max, obviously over theta 1 up to theta k and omega 1 up to omega k. Sorry, I should have used hats everywhere to indicate that these are my estimators for the parameters. So I'm going to compute this as the argmax of a function that I'm going to call q. And this function q is, of course, a function of theta 1 up to theta k and omega 1 up to omega k. But it's also going to be defined in terms of the previous values of these MLE's estimators. So to construct the next iterate of the algorithm, we start in some sense with the previous value of the iterate. That previous value of the iterate allows us to construct this function q that ends up being maximized to obtain the next iterate. And the way in which this function q is constructed is very simple. So this function q of theta 1 up to theta k and omega 1 up to omega capital K, given the previous iterates, is defined just as an expected value of the log likelihood, so the log of the distribution of my data given my indicators C1 up to Cn, and my parameters theta 1 up to theta k, and this expectation is taken with respect to the distribution of the vector C, the vector that contains all the indicators, given the previous values of the iterates. So this will become a little bit clearer once I do an example with a particular kernel, but the idea is relatively straightforward. So you're going to have a guess at what the components each observation belongs to, and that guess is based on your previous values of the parameters. And given that guess, you're going to construct this function q and maximize the function q to get a new estimate of the parameters. And then you just repeat the process. You're going to use this new guess, so this new estimate of the parameters, to create a new guess at what the values of the C's are. And given that guess of the values of the C's, again, construct a new q and maximize that new q to obtain the results. Just to clarify, this expression down here, so this expected value is relatively easy to compute, because remember that the C's are discrete random variables that just take the values from 1 to k. So really what I need to compute is so to compute this expectation, what I need to know is what is the probability that C sub I is equal to k, given the previous values of the parameters, given those vectors thetas and those vectors of omegas, my previous estimate for those. And the expression is relatively simple because you can basically compute it using Bayes' theorem. If you think about what the probability that C sub A is equal to k given the parameters and the data, you can just compute that as the probability of the data given that C sub I is equal to k, which just becomes g of sub k of x sub I given my weight theta hat s sub k multiplied by the prior, that is omega sub k s, and then renormalized over all the components. So from L equals 1 to capital K of G sub L x sub I given theta L hat S WL S. So basically we're saying that the probability that the observation comes from component K is higher if the likelihood of the component K evaluated in that observation tends to be higher than the likelihood for every other component. So this gives you the probability that each observation comes from each component, and then this probability can be inserted in this expression to compute this expectation. So you can clearly see now that this expression, it's going to depend both on the values of theta and omega, but it's not going to depend on the so it's going to depend on the previous values, and it's going to depend on the values that you're going to try to optimize, but it's not going to depend on C because you will be integrating over that parameter. Let's discuss the structure now of the EM algorithm for particular mixture models, first in general, and then we'll carry out a particular example with a mixture of normals that I'm hoping will help clarify some of the concepts. So we just discussed the structure of the function Q. We also discussed that the probability that C sub I is equal to K, so that observation I belongs to component K, given my current value of the parameters theta and omega, can be obtained as a simple application of Bayes' theorem as the ratio of omega sub k hat s times g sub k of x sub I given theta sub k hat s divided by the sum of omega L hat s g sub L x I given theta L s hat as that set of weights. Once we have this probability, the other piece that we need to write the function Q is the log likelihood of the data, or the complete data log likelihood. So that's just the logarithm of the expression that we had discussed a couple of lectures ago that depends on both the data and the CIs, and that has a very simple expression in this case. It's just the likelihood, or the complete data likelihood, for the parameters theta 1 up to theta k and omega 1 up to omega k and C1 up to Cn. Remember that I want the log, the complete data likelihood. This is the product from I equals 1 to n of the product from k equals 1 to capital K of omega k g sub k of x sub I given theta k raised to the indicator that C sub I is equal to k. Once we have these two pieces, we have the probability of the C sub i's, and we know what the complete data likelihood looks like, then we can proceed to compute the Q function for our mixture model. For simplicity, I'm gonna rename this whole expression with a slight shorthand. If you think about this expression, it depends on the observation, it depends on the component, and also depends on the step of in which you are in your algorithm. So let me call this BIK of S for short, so that I can write a little bit less. So what we need to do to construct the Q function, which is a function of the thetas and the omegas conditional on the current value of the parameters. And omega 1 hat all the way to omega capital K hat. We are going to need to take the expected value of the logarithm of this expression. So that's what the Q function is. So this is going to be the expected value with respect to this distribution up here of 1, or the indicator, excuse me, of C sub I equals to K, multiplied by the logarithm of omega sub K plus the logarithm of G sub K of Xi given theta K. Now, this expectation is very easy to compute because and of course, so this is the expectation for a single one, but in general, I need to compute the sum over all the observations in all the components. So we're going to have the double sum of the expectation from I equals 1 to n and from k equals 1 to capital K of those expectations. Now, as I was saying, this expectation is easy to compute because really the only piece in here that depends on C is this indicator function that is here. So for the purpose of computing the expectation, I can treat this piece as a constant. So this just becomes, again, the double sum from k equals 1 to capital K and from I equals 1 to capital N of the expected value of these indicators multiplied by the same expression, the logarithm of omega sub K plus the log of G sub K X sub I given theta K. In this expectation, it's the expectation of an indicator. By definition, the expectation of an indicator of an event is just the probability of that event. And so that just means that this expected value is simply this value Bik of S that we had just computed up here. So the Q function actually has a very simple expression. The Q function can be written just as this weighted sum, where the weights are given by the B sub I case, of actually two terms that are split off. So one term has to do just with the prior probability, so the weight of each one of the components, and another piece that has to do with the likelihood of the case component. So that means that if the structure of this function G sub K is relatively simple, then the fact that we are just using a weighted average will allow us to basically extend the way in which we do estimation for theta K in the regular parametric model to the way in which we will do the inference for the case component of this complicated mixture. And now what we'll do is we'll proceed to clarify these ideas a little bit by essentially deriving the algorithm for a mixture of normals, where the particular structure of the G sub K allows for that kind of simplification that I was just discussing.